It would begin in seconds, but the destruction would feel unreal. A single asteroid entering Earth's atmosphere at cosmic speed could unleash the force of a nuclear scale blast, shattering windows, flattening forests, and sending shockwaves racing across entire regions. Humanity has already seen warnings of this danger. The 1908 Tunguska event devastated a vast area of Siberian forest, and the 2013 Chelyabinsk airburst injured more than 1,600 people, mostly from shattered glass and blast effects. Earth has never been sealed off from space. It lives beneath a sky filled with ancient debris, and every so often, one of those rocks reminds us how exposed we really are. That is what makes the threat so terrifying. The next object may be larger, faster, and aimed more precisely at where people live. And when that moment comes, survival will depend on one thing alone: whether humanity learned how to stop it before it ever reached us. That is the point where fear became policy. NASA could not wait for the perfect asteroid emergency to arrive before deciding what to do. It needed proof, real proof, that humanity could actually change the path of a dangerous object in space. That is why NASA created DART, the Double Asteroid Redirection Test, the first full-scale mission built to test whether a spacecraft could strike an asteroid and push it onto a different course. It was not designed to destroy a world-threatening asteroid in panic. It was designed to answer the question before the emergency came: if a deadly rock were ever heading toward Earth, could we reach it in time and move it just enough to save the planet? For NASA, DART was more than a mission. It was the first serious attempt to turn planetary defense from theory into something humanity could actually use. But NASA could not prove planetary defense by aiming at a rock that was actually coming for Earth. The risk would have been too great, the stakes too high, and one failure could have turned an experiment into a disaster. So instead, they chose a target that was safe, close enough to observe, and scientifically perfect: the Didymos-Dimorphos system. Dimorphos was the smaller body, only about 160 meters wide, orbiting the larger asteroid Didymos, which is about 780 meters across. That made it ideal. By striking the smaller moonlet instead of the main asteroid, scientists could measure whether its orbit changed after impact. In other words, this was not just about hitting a rock. It was about proving, for the first time in human history, that we could move an entire world in space on purpose. That is why NASA chose Dimorphos, not because it was dangerous, but because it was the safest place to test humanity's first real planetary defense weapon. That was never the plan, because destroying an asteroid is often far more dangerous than moving one. It sounds simple in movies: blow the rock up, save the world. But in real planetary defense, fragmentation can make the problem worse. Instead of one incoming object, Earth could end up facing a cloud of unpredictable debris, each fragment following its own path. NASA needed something smarter, more controlled, and more realistic. That is why DART was built as a kinetic impactor, a spacecraft designed to slam into an asteroid and nudge it, not shatter it. In simple terms, a kinetic impactor uses speed as a weapon. The idea is not to destroy the target, but to change its orbit just enough that, years later, Earth is no longer in the way. That is what made DART so important. It tested whether precision could protect a planet better than brute force ever could. On September 26, 2022, DART finally reached Dimorphos and did exactly what it had been built to do. It hit.
3, 2, 1. Oh my gosh.
Oh, wow. Awaiting visual confirmation.
All right. Let's see. We got it?
The spacecraft, about the size of a vending machine, slammed into the asteroid moonlet at roughly 22,530 kilometers per hour. But the most surprising part came afterward. Scientists had expected the impact to shorten Dimorphos's orbit around Didymos by at least 73 seconds. Instead, the change was dramatic. The orbital period was shortened by about 32 minutes, later refined to about 33 minutes and 15 seconds. That result meant the mission had worked far better than the minimum success goal. And the reason was fascinating. DART did not simply punch the asteroid. The collision blasted huge amounts of rock and dust outward into space, and that ejector acted like extra thrust, giving Dimorphos an even bigger push. In other words, the asteroid's own debris helped move it. If DART proved that deflection works, the next question became even more important. Exactly why did it work so well? That is where the aftermath becomes just as important as the impact itself. Scientists still need precise answers about the crater, the asteroid's internal structure, its mass, and how momentum moved through Dimorphos after the collision. That is why the European Space Agency launched Hera in October 2024. Hera is now heading toward the Didymos-Dimorphos system and is expected to arrive in late 2026, where it will study the damage in detail and help turn DART from a dramatic success into a reliable planetary defense method. And the aftermath has already grown even bigger than expected. Newer analysis shows DART may not only have changed Dimorphos's orbit around Didymos, but also slightly changed the binary asteroid system's path around the Sun. That is a historic first. Humanity did not just hit an asteroid. It may have measurably changed the solar orbit of a natural body. That is what makes DART so important. The mission was not truly about one small asteroid drifting harmlessly through space. It was about the next one, the one that might actually matter. NASA has long understood that the most dangerous objects are not always the largest ones. A giant dinosaur killer asteroid is rare, but smaller near-Earth objects, often called NEOs, are far more common. A NEO is simply an asteroid or comet whose orbit brings it close to Earth. Some of them are large enough to destroy a city, devastate a region, or trigger global consequences if they strike in the wrong place. DART was designed as a test for exactly that kind of threat. Not the end of the world in one impact, but the kind of impact humanity could realistically face in the modern age. In other words, Dimorphos was a rehearsal target. The real audience for DART was every future asteroid that may one day appear on a collision course with Earth. That is the uncomfortable truth at the heart of planetary defense. Even the best deflection mission is useless if the threat is discovered too late. DART only works as a strategy if humanity has enough warning time to launch a spacecraft, reach the asteroid, and change its path years before impact. That is why planetary defense begins not with rockets, but with detection. NASA and its partners spend every year scanning the sky for near-Earth objects, building catalogues of potential threats, and calculating whether any might one day cross Earth's path. That work is now moving into a new phase with NEO Surveyor, a powerful infrared space telescope designed specifically to find dangerous asteroids that ordinary visible light surveys can miss. Infrared matters because dark asteroids may reflect very little sunlight, yet still glow in heat. For the first time, humanity is not simply vulnerable to the cosmos, it is beginning to answer back. But the danger has not disappeared. Asteroids are still out there, ancient, silent, and indifferent to life on Earth. The difference now is that we are finally building the tools to face them. DART was not the end of that story. It was the first real signal that when the next dangerous rock appears, Earth may no longer have to stand there helplessly and wait.